Okay, let's start today's lecture 5 of the course. So yesterday we stopped talking about whether one should fit spiral arms or not, and the general advice was that you don't, because it increases the number of free parameters quite drastically and then makes the fit very unstable. So you can subtract out the smooth components that will identify for you the spiral arms and other non completely axisymmetric structures, and then you can do photometry on them. You can do any kind of measurement you want on them. The same holds for fainter galaxy components such as shells and halos. We saw some examples of shells and rings and so on, and these are very faint, too faint to fit. And yesterday, in response to one of the questions, I spoke about the stellar halo and said that the stellar halo is definitely there. It's an important component. It often contains the oldest stars in any galaxy, but it's just too faint to fit. But it may be seen in the fit residuals. Sometimes if you have a fairly strong halo, then once you subtract out the bulge, you may be able to see the halo in the residue. So as I remarked in the first lecture, the fainter you go, the more you see. So this is again an example from a paper by Duke et al. 2011, wherein they use the Canada-France Hawaii telescope at Mauna Kea to do extremely faint low surface brightness imaging using a camera called MegaCam, which is a very, very special sensitive camera. And this telescope is located at one of the finest locations, very dark skies, very stable atmosphere. And that allows you to reach these very low surface brightness levels, even with a telescope that is not too large. So these are all examples of nominally early type galaxies, which means ellipticals or lenticulars. I think this object at the bottom may have a disk, but most of the others are all elliptical galaxies. And you can see that there's there are a lot of stars outside. Remember, the emission that you see on the outside is not gas. It is the light coming from stars, right? Because gas doesn't emit in the continuum like this. So these stars have somehow been thrown out of the galaxy. And as we shall see later, at least in early type galaxies, this type of structures are indicative of mergers, both minor mergers and major mergers, which lead to such structures. We know that from numerical simulations, that tidal effects tend to disrupt a few stars, throw them out of the galaxy. These structures are also indicative of relatively recent mergers, because once a few billion years pass by. Sorry, was there a question from anyone?
Yeah. Sir, I think you have not shared the presentation on Zoom.
Okay, thank you. Yes. So please, if something like this happens in the future, are you able to see it now?
Yes, sir.
Yeah. So please interrupt me right away if something like this happens. So these are all early type galaxies, elliptical galaxies in general. And they have all of these extra structures, which are very low surface brightness, because there's a very low stellar density. So stellar density here is measured not in terms of stars per unit volume, but stars per unit cross-sectional area, right? And so that is also very low in these structures. So only when you image to extremely faint levels do you even see these structures. But now what subsequent to this work, which is about 10 years old, several other groups and the same group of people have done additional observations, and we are finding quite commonly that structures like you see in this galaxy are seen around most elliptical galaxies. Not totally surprising, but indicating a merger-based history to mergers playing an important role in the formation of elliptical galaxies. Okay, so we've looked at quantitative morphology, particularly of one kind, which is trying to do analytical fits to the different components of galaxies. So there are limitations here, obviously. One obvious limitation is how can we be sure that the analytic representation that we have chosen is a correct and complete representation of the light distribution. So suppose we use an exponential to model a disk. Suppose the disk is not exponential, okay? Or it's a double exponential disk and we have used only one function to fit the entire disk. So it may not be correct, it may not be complete representation of the true light distribution. And as we already saw, if we try to add analytic forms for spiral arms in the bar, the additional free parameters can introduce degeneracies in the fit. So the accuracy of parameter estimation is strongly dependent on the accuracy of the point spread function determination and the sky estimation. I spoke a little bit about sky estimation in response to a question yesterday. So if you get the sky wrong by even a few %, you can make very large errors in your estimation of the bulge and disk parameters. So what is the lazy person solution in this case? Use Hubble Space Telescope data, because Hubble Space, once you go above the atmosphere, the air glow goes away. The atmosphere, the sky background with Hubble images in the visible band is 100 times fainter than the best sites, meaning zero light pollution sites on Earth. So it's still 100 times better because there's no air glow. And of course, there are some other extra atmosphere sources of emission like the zodiacal light, which is the brightest. But other than that, there is little else. More importantly, we don't have any atmospheric scattering above the atmosphere, obviously. So even if the moon is there somewhere in the sky, it doesn't affect the observations made with the Hubble Space Telescope. So the background is low, it's completely stable, it's completely flat, and more importantly, the point spread function is very well determined, because unlike on the Earth, where the observed point spread function, what is meant by the point spread function? Suppose you observe a point source like a star, what does its image look like? So obviously that is not a single delta function like function, but it is a spread out function. Moffat function we saw yesterday is one approximation that's available. A very cruder approximation is the Gaussian, which is also used by many people. But the atmospheric conditions can change from hour to hour, sometimes minute to minute. And therefore, the point spread function can change in width quite dynamically. So measuring it accurately becomes quite tricky. With the Hubble Space Telescope, you don't have to worry at all about the point spread function, because the point spread function is only determined by the diffraction from the optics of the telescope, which are very well modeled and understood. So you don't have, it's very, very well determined. And therefore, your accuracy of the galaxy parameter estimation improves a lot, particularly for very distant galaxies. Remember, when the galaxy is very distant, it's going to become small in angular size. And therefore, its size may become comparable to the size of the point spread function. On Earth, it may be even smaller than the point spread function. Then you say the galaxy becomes unresolved. But with HST's small PSF, it usually is resolved. But so that also helps, having a smaller PSF. Okay. So In spite of these limitations, quantitative morphology is widely but not always wisely used today in many studies of galaxy evolution. So you will see literally 100 papers a year that use these kind of decompositions in order to test the comparison of, test the predictions of various models against the observed universe. When you do the bulge-disc decomposition, you should establish some quality control norms. So the reduced chi-square is a good quantitative goodness of fit indicator. Okay, so depending on the degrees of freedom, which means the number of free parameters that you have and the number of individual pixels that you have, the reduced chi-square should come out close to 1. That means you are within the noise you attained a good fit. In addition, the fit diagnostic plots that we used can be used to evaluate the quality of the fit. Are the residuals small and random? Is the residual histogram at least approximately Gaussian? And does the radial profile pass through the azimuthally averaged data points? And has the masking been done correctly? So if you take care of all of these points, then your chances of getting a good fit increase drastically. There are a number of bulge-disc decomposition codes that are available. I wrote one of the earliest ones. In fact, my first paper when I wrote my thesis, when I was doing my thesis, was on one such code. It uses something known as the Davidon-Powell-Fletcher variable metric algorithm to actually perform the fit. It's very fast, but it has not been maintained for a very long time. So although it was used in the first 5 or 6 years, after I stopped maintaining it, people stopped using it. Now, the sort of market leader in this is a code called GALFIT. It was written by Peng and collaborators in 2002. It's by far the most widely used code. It's very fast because it uses a very simple and very fast algorithm called Levenberg-Marquardt. It's really awesomely fast. More importantly, it has been continuously maintained since the code came out around 2002. Peng, in fact, has a Facebook page where he personally answers questions about the code and about the fitting. Then there's one called GIM2D. It uses an algorithm called Metropolis, which is similar to an algorithm called simulated annealing. It's very slow, but it is very good if you have extremely low signal to noise images, very, very faint galaxies, then it will likely do a better job than GALFIT. But for nice nearby bright galaxies, GALFIT works perfectly well. Then there is a code called Buddha, D'Souza et al. 2004. There are some newer codes, so I should probably update this list and add a few more codes. But there are at least 4 or 5 codes that have come out in the last 10 years. And some of them are quite good, but still GALFIT sort of maintains its lead as the most preferred decomposition code. GALFIT has one advantage, that it can fit multiple galaxies simultaneously. So what you see on the left side is like 5 different galaxies, part of a group, and GALFIT can fit all of them together. So it fits Sersic bulges and exponential disks and point sources if you want, or any other component simultaneously to all of these 5 things. So what you see there is the model, and on the right panel is the residual, which is sort of noise-like, indicating that you've got a good fit. So some 10 years back, a student from MG University, Kottayam, and me and Ajit Kembavi and a few others, we wrote a pipeline called PyMorph, So what it does is it basically can operate in two modes. One is when you give it a large number of cutouts, which means small postage stamp images of galaxies, or if you give it just one big image and run it in a sort of find and fit mode, wherein you just tell it that, okay, find all the galaxies brighter than a certain magnitude or greater than a certain size in this image and fit it. So it goes and does everything automatically. Now, this code has been used on very, very large survey data, including the SDSS, primarily because Vinu, who was the first author of this work, went and did a postdoc at UPenn, and when he was there, he ran it on 700,000 galaxies. So it's been quite heavily used, this pipeline. It also runs, in addition to the bulge-disc decomposition, of course it does, since it uses GALFIT underneath, it does the nearest neighbor object fitting also quite nicely. But we also added in a non-GALFIT component to it, which is something known as the non-parametric parameter estimation, non-parametric fitting, and that I will talk about in this lecture in a minute. So all of this is there in the code. This code is still being maintained at some level and is being used, especially by people who don't want to fit one galaxy but thousands. So obviously this whole game breaks down when we go to high redshifts. You don't see that elliptical shape, you don't see the clear lenticular shape, nothing. It's all objects that are funny looking. And this is already at redshift 1, where 30% are peculiar. Once you go to redshift 2 or 3, 100% of galaxies are peculiar. They can't be called ellipticals or spirals. So in such cases, a different technique, so you can't do your regular bulge-disc decomposition at all. A new technique called non-parametric estimation was developed, and there were basically two kinds of measurements that were done. One is called CAS, and the other is called GM. Okay, so let's look at CAS. So there is something known as the concentration index. It's defined as the ratio of the radius of the galaxy, which contains 80% of the total light, to the radius of the galaxy, which contains 100% of the total light. So it's defined like that. Of course, it's a log scale. Now, the problem arises how to consistently define the total light of a galaxy. When you're doing a bulge-disc decomposition successfully, then we saw yesterday, you can simply integrate it out to infinity to get the total light. But this kind of technique is used when you can't do a bulge-disc decomposition successfully. So you're sort of stuck. So what do you do? How do you define the total light of a galaxy? That is done using a concept known as the Petrosian radius. So the Petrosian radius is the radius of the galaxy in which the Petrosian parameter eta takes a value of 0.2. And the Petrosian parameter is defined as follows. It's the ratio of the average light at the radius r, and IR is the average light inside. The denominator is the average light inside R. Okay, so you keep on going outwards and keep measuring the Petrosian parameter. When you are, it will move, it will change as a function of radius, and eventually you'll reach a state where it crosses 0.2. And then you say, okay, this radius corresponds to the Petrosian radius. And then you just adopt just arbitrarily you say that the total light of the galaxy is defined as the light within 1.5 times the Petrosian radius. So you measure up to the Petrosian radius, then go 1.5 times and do what is called aperture photometry over that aperture. And you say that, okay, anything, any of the galaxy light that lies within, I will count, and I'll say this is the total light of the galaxy. The only thing that is important here is that everybody chooses a Petrosian parameter, the definition of Petrosian radius to be the same, and everybody chooses to use this number 1.5. Somebody does, instead of 1.5, does 0.5 or 2.5, there'll be trouble. So, so long as people standardize on that, the Petrosian radius concept allows you to measure the light of a galaxy without, in a sort of non-parametric way. There's no fitting involved, there's nothing, there's only a measurement. Yeah. Sorry, if the galaxies? Yes. Correct. So how do you determine the center? That's a very interesting question. So usually what people adopt is that you centroid the image of the galaxy. So you take a weighted average of the intensity distribution. So even if the galaxy doesn't have a well-defined center, by centroiding over the entire galaxy, you'll be able to find the nominal center, which you will have to use when you are determining the Petrosian radius. And it's not that they're irregular. I should clarify that they are not completely regular. They do have some shape, but that shape is not completely symmetric. See, remember, a regular elliptical galaxy has a 180-degree symmetry about it. You rotate it by 180 degrees, it should look exactly the same. That's a regular elliptical. But here they won't have that kind of symmetry. Okay. So now the question is, how does concentration index act as a proxy for the morphology? Naturally, we saw the light profiles yesterday. We saw that if the Cercic index is very high, the galaxy will have a very steep light profile in the inner parts. This indicates that its concentration will be higher because there'll be more light concentrated near the center. So it can be shown that the concentration of an elliptical galaxy, that is a galaxy with Cercic index n equal to 4, is 5.3, and that of a pure disk galaxy is 2.8. Pure exponential disk, no bulge at all, it's 2.8. Therefore, the concentration index is related to the bulge to total luminosity ratio in a monotonic way. Also, it can be shown that the concentration parameters related to the Cercic index, as the ellipticals have larger value of the index than disk galaxies. These correlations make the concentration a useful non-parametric way to classify galaxies. So there will be three-way analytical relation between the bulge to total ratio, the Cercic index, and concentration. So these three things, so when you measure concentration, you measure bulge to total ratio and Cercic index in a sort of degenerate way. So if you know one of them, you can determine the other. So that's the idea behind using this concentration index. And the important thing to remember, this is a non-parametric. By parametric, one means when you fit a parametric function to some data. Here we are not fitting any function. We are just doing measurements, which are easier to do. Fitting nonlinear data can be very difficult and problematic. That's why the non-parametric way works even when you have relatively poor quality data, or there are some other problems with the data itself. So here is, if you do that three-way relationship between concentration index, B by T, and N. So as I said, for a given concentration index, you will have a curve that represents. So this is the concentration index, and B by T and Sersic index on the right. So there'll be a degenerate curve that on the Sersic index B by T plane, and that curve, if you know either the B by T or the Sersic index through some independent way, suppose you happen to know that this is an elliptical galaxy, so the B by T is 0, you'll be able to read off what is the value of the Sersic index from this plot. Okay. The next parameter, so what we are studying now is something known as CAS parameters: concentration, asymmetry, and you'll see what S means in a minute. These three together can be used as an effective proxy in place of the bulge-disc decomposition outputs. So asymmetry is a simple idea. We rotate the galaxy through 180 degrees using bilinear interpolation about its center, which is taken to be the centroid. So in answer to your question, the first image moment of the galaxy pixels is taken as the center by centroid. In the next step, we subtract the rotated image from the original image of the galaxy. And from the residual image, we estimate the total residual flux inside the extraction radius. This is then normalized by the total flux of the galaxy. This step can be represented as follows. So you basically original image minus the rotated image divided by the original image. And the summation is over all pixel inside the radius R, RT. So now what to choose as RT? Most people choose the Petrosian radius itself as the RT. And you then basically rotate the galaxy, centroid it within the extraction radius, rotate it by 180 degrees, subtract it, and measure the flux in the residue. So now what will be the asymmetry of a perfect elliptical galaxy? 0, right? That's correct. So the ellipticity of a perfect elliptical galaxy is going to be 0. And a spiral obviously does not have 180 degrees rotation symmetry. So it will show a high flux value. And of course, galaxies that don't have any symmetry, like regular galaxies and so on, are going to show a very high value of asymmetry. Yeah. So this is what we saw. How is asymmetry connected with morphology? Then clumpiness. Okay. And they take the S from the last letter or second last letter of this. So that gives us the CAS parameters. So CAS parameters are concentration, asymmetry, and clumpiness. To find the clumpiness S, we convolve the galaxy image with a boxcar function of width 0.5 Petrosian radii. This smoothed image is then subtracted from the original image, and the residual is summed within the extraction radius. The output of this process is the sum of clumpiness of the object and the background, right? So you have clumpiness defined in this way, where I0 is the original image, IS is the smoothed image, and the summation is over all the positive pixels of residual image within the annual region of width 0.2 to R to R extraction, RT. Okay. So now this is going to measure clumpiness. So how is this going to be related to morphology? What will be the clumpiness of an elliptical galaxy and a spiral galaxy? Sorry? Yes. And what will be the clumpiness of elliptical? Perfect elliptical? Yeah, it will tend to 0. Okay, it will be very close to 0 because there are the smoothed version and the original version would be very similar to each other. If you subtract one from the other, you'll get 0. And then the numerator of this equation becomes 0. So clumpiness will become 0. So now what we've done is we're not measuring the bulge and the disk components separately and so on, because they don't exist at those redshifts. So it has been shown, for example, people, so what I've been talking so far about these bulge and disk structures as if they are only physical structures in the sense of how the galaxy looks. But these are also kinematic structures, which means the bulge and the disk rotate in different ways. The stars in them move in different kinds of orbits. So when we study kinematics and dynamics, you realize that the bulge and the disk are not just structural components in how the light is distributed or how the stars are sitting inside the galaxy, but it is also a kinematic component which tells you more about how the stars are moving inside the galaxy. So therefore, it's important to keep that in mind. And that is why the importance of studying the bulge and disk becomes even more important. That these are not modeling just how the stars are distributed, but how the stars are moving, because how the stars are moving also determines for you how the galaxy is going to evolve. Therefore, the evolution of the disk and the evolution of the bulge can be very different. Also, because the stars are moving differently, they obviously have different angular momentum. They also tell you about how they formed in the first place. The disk stars form from the high angular momentum component of the gas in the galaxy, whereas the bulge stars form from the more random angular orientations of the underlying gas that forms the stars in the bulge. Okay. Right. So these are the gas components. So what we did, we a bit of cheating. We don't have the bulge, we don't have the disk as we know it. But can we find analogs of this at high redshift, that we can measure some parameters that will help us to classify galaxies? So with CAS, one could basically have a three-dimensional space, CAS, and we just say that, okay, these kind of galaxies sit in this region of the parameter space, which in the low redshift universe is similar to ellipticals, and these set of galaxies sit where spirals sit today, and so on. So you don't call them ellipticals or spirals because that is inappropriate, but you try and gain some understanding of what kind of these objects these things are by using these CAS parameters. Now there are two more parameters. One is called the Gini coefficient. Okay. So this Gini coefficient doesn't come from astronomy, it comes from economics, so the statistical economics. So in economics, they like to measure this coefficient to find out how uniform or non-uniform the wealth distribution is in any given society. Okay. So they measure, so for example, if all the wealth is concentrated with one person, then you'll have one extreme of the Gini coefficient. If you have total socialism, everybody has equal wealth, then that will be the other extreme of the social perfect equality versus perfect inequality. So here, instead of doing it with the money distribution, we do it with light distribution, but the definition is the exact same otherwise. So to get the Gini, we first find the pixels in the image which belong to the galaxy. That is, obtain the segmentation map of the galaxy. And so how do you obtain a segmentation map? How do you decide whether a particular pixel is part of the galaxy or it's outside the galaxy? You typically do that by doing this kind of boxcar filtering. So you convolve the galaxy image, so you smooth it. What that will do is that will redistribute the light in the outer parts of the galaxy in such a way that it will increase the signal to noise in the outer parts of the galaxy. So what we are doing here, we are sacrificing resolution for improved signal to noise. Then we measure the intensity I Petrosian at R Petrosian. We assign all the pixels in the image with IP less than I less than 10 sigma to the galaxy, where sigma is the standard deviation of the sky. So normally, the one standard way in which you decide whether a pixel belongs to an object or not is to compare the standard deviation of the, or the value that you measure in the pixel with the random distribution of the sky background. So if it's more than 10 times higher than, if it's more than 10 sigma above the sky background, that indicates to you that this is unlikely to be a random fluctuation in the sky background measurement, because the probability of getting a 10 sigma fluctuation in a Gaussian distribution is very, very small. So that's the idea. The upper limit ensures that no cosmic rays or spurious pixels are included in the segmentation map. Okay. I Petrosian less than 10 sigma. So you start with the intensity at the Petrosian radius and go up to 10 sigma, which is very high. So actually, I'm sorry, this 10 sigma is an upper limit, not a lower limit. So take back what I just said. It's an upper limit because you want to exclude cosmic rays or other such spurious pixels that may be included in the segmentation map. Then the pixels belonging to the segmentation map are sorted according to their photon count, and the Gini coefficient is calculated according to this particular equation. Okay, so these are all measured parameters: the photon counts in the pixel I, the mean count in all the pixels, and the total number of pixels, and so on. So if you fill it in there, you get the Gini coefficient. How will Gini be affected if we get the segmentation map wrong? So suppose you, instead of using 10 sigma, you only include pixels up to 5 sigma. Will the Gini coefficient change or not change? It'll change because you'll exclude the most unequal pixels, right? So it will increase the equality apparently because you've thrown out the most unequal pixels. So getting the segmentation map wrong will change things, either increase or decrease the Gini coefficient, depending on whether you include or exclude bright or faint pixels. Will the Gini coefficient be higher in ellipticals compared to spirals? So for that, you have to go back here. Okay. So now, so what you're doing is, let's look at the equation. So if all pixels are completely equal, let's take an extreme case. All pixels have the exact same value. Then 2 times I to the segmentation map. So you'll get a value of 2 times the number of pixels here into ij divided by n, which is the total number of pixels. So you'll get, I think, a value of 1. We'll have to check that if you have complete equality. And if you have complete inequality, then it will go to 0. And so where will there be more? Let's not worry about the actual value. Which ellipticals will have more equality, or spirals? Ellipticals will have more equality, right? So the Gini coefficient will indicate a more equal distribution when you look at elliptical galaxies. Okay, so there is the last parameter that we look at. These are now called GM parameters, Gini and M20. It's the second order moment of the brightest pixels. This quantity measures how the brightest pixels are distributed over the galaxy segmentation map. We use the same segmentation map that was used to measure the Gini coefficient. And we start by computing the flux-weighted second order moment of the galaxy. Okay, so which is defined here. And then we minimize MT with respect to the center of the galaxy, with the initial value of the center being the centroid. So you actually move the centroid around so that you minimize this second order moment. Okay, and that process converges very quickly, and you get a centroid, a new centroid, and a new, of course, the lowest possible MP value. Then what you do is, to measure the M20 index, we sort the pixels according to their flux value and find the moment of the 20% brightest pixels of the galaxy using this equation, where the summation continues till it satisfies II less than 0.2 IT, where I is the pixel in the sorted array of the segmentation map, and IT is the total light of the galaxy, till you contain 20% of the total light of the galaxy. Yes. So with the new center, so you always measure everything with respect to the new center. Center, like I was telling her earlier, it's very hard to determine the center uniquely. Okay, and no, I mean, the moment has to be minimized, the second order moment. Normally, what we do when we determine a centroid, we are basically minimizing the first order image moment. That doesn't mean that it also minimizes the second order image. That's the difference. So, okay, now M20 index. Question: if you observe the same spiral galaxy in a blue and red filter, where will the M20 be higher and why? Is M20 similar to the concentration parameter? So let's take the first question first. You are observing a spiral galaxy in blue and red filter. Okay, same galaxy you observe in the blue filter, and then you observe it in red filter. Where will the image moment be higher? younger and brighter stars. In a spiral galaxy, where are they located? In the spiral arms, correct. So when you observe it in the blue filter, you will prominently see those spiral arms. Sorry? No, the image moment, will it be second order moment? Will it be higher or lower in the blue filter? Let us do a simpler thing. Take a perfect elliptical, take a perfect spiral, okay, same size, etc. Where will the M20 be higher? For an elliptical, 20% of the brightest pixels are sitting where? Right at the center, just that central region. So that image moment, second order moment, will be small because the radius will be small. So obviously, ellipticals will have a lower M20 value than spirals. Now that may help you understand what it will be for second order image moment for red and blue filter. Huh? Blue will be higher because more of those H2 regions will become prominent. In the red filter, they will fade, and some of them may just drop out outside your 20% value, and then you will get weighted by the center of the spiral is also bright. There's no doubt about that. So then the central pixels start appearing in your top 20%, and therefore your image moment drops. So definitely the blue filter image will have a higher value of M20. Is M20 similar to the concentration parameter? Yes, in some sense, because you're seeing how concentrated. If the light is very concentrated, then the M20 value is lower, as opposed to the light being less concentrated, like a spiral galaxy, the spiral arms, bright spiral arms. So yes, so M20 is related to concentration. Sorry? Not exactly, because they are not equivalent to each other. They are not exactly equal. Okay, I thought I had included one more slide here, but I will just open the next lecture. Okay. So how does Gini M20 help you in understanding galaxy evolution? Okay, so what you have here is the M20 parameter on the x-axis, but increasing towards the left, and the Gini parameter on the y-axis, increasing towards the top. And if you take local galaxies and measure their Gini and M20 parameters and place them in this plot, then they actually nicely partition like is shown in the figure. A high value of Gini coefficient indicates mergers, and accompanied by a high concentration of a high value of M20 as well. Okay. A low value of M20 can still correspond to a merger, provided the Gini coefficient is very high. Okay, so these are at the top right corner. But over here are your Milky Way like spiral galaxies, which have low value of M20, okay, and a relatively low value of G, or intermediate value of Gini. They're not really low. There are no galaxies here. If you go to these late type and irregular galaxies, they have a very high value of M20, as the star formation is happening everywhere in the galaxy. So you will have not at the center. In fact, it's not centrally concentrated at all in a regular galaxy. So they will have a high value of M20, but the Gini coefficient will be very low. So I think a low value of Gini coefficient indicates equality, not inequality. So we made an error in that equation. We have to check that. So a low value of Gini coefficient indicates extreme inequality, and a high value indicates complete equality, and it goes from 0 to 1. M20 is also a ratio, it goes from 0 to 1. So for high redshift galaxies, we can make a connection with what is happening in the low redshift universe via this M20 diagram. And for the CAS parameters as well, we can do the same. So instead of a 2-dimensional figure, it will be a 3-dimensional plot. And you can see that galaxies of a particular morphology will cluster in this space. Here, mergers are quite important at high redshift because we know that at a redshift of about 2, many things peaked. So we have a peak in the activity of quasars. So the maximum number of galaxies have active nuclei at redshift about 2, 3 in that range. At the same time, we have very high star formation rate density in the universe. So the maximum number of stars are getting formed normalized by co-moving unit volume, per co-moving unit volume, than any other time in the history of the universe. And now with these kind of studies, it's also becoming clear that the merger rate was highest at these epochs. So therefore, a lot of the merger, and all of these 3 things are correlated, right? The merger leads to a lot of collisions of gas and increased star formation. Mergers also lead to merger of supermassive black holes and the growth of AGN activity, primarily because in that process of churn, a lot of gas gets fueled towards the center. So there is enough food available for the black hole to swallow and remain as an bright active galactic nucleus for a very large period of time and grow the black hole mass very rapidly. So this is a time of growth of the stellar mass due to enhanced star formation. There's also a period during which the mass of the supermassive black holes increases rapidly, both due to mergers. So because when 2 galaxies merge, their supermassive black holes are also going to merge with each other. And those supermassive black holes, both of them, and then once they become one big black hole, are going to swallow a lot of matter that's there in the merging galaxies. And so mergers will also be, and the Gini coefficients is one way of measuring the merger rate via a proxy, of course, but measuring roughly whether the merger rate is enhanced at different redshifts. So you can take a sample of galaxies for redshift 1, 1.5, 2, 2.5, and 3, and measure the Gini coefficients and M20 parameter for all of them and see where they move on this 2-dimensional diagram. You could do the same with the CAS parameters, see how they move on those CAS parameters space, and use that to constrain the merger history of the underlying population. So that's the efficacy, that's the utility of these things. I think, yeah. So I'll just introduce this slide and stop. So far we have looked at galaxies as individual units. Okay, and we have spoken a little bit about their constituent subunits, which are stars primarily. But we said in the first lecture that the atomic units in the universe are atoms, stars, and galaxies. And once you come to the scale of the universe, the galaxies become the atomic units that you want to look at. So far we have looked at each galaxy and its subcomponents. The physical scale of this is a few tenths of parsecs. But now we need to look at the large scale structure of baryons in the galaxies on megaparsec scales. So we are just going to jump from kiloparsec or few tens of kiloparsec scale to a scale that is 100 times larger, the megaparsec scales. And just as stars are the individual building blocks of galaxies, galaxies are the building block of the cosmic web of large scale structure. Why is it called cosmic web? Because it looks like a spider's web. It is connected in 3 dimensions like a spider's web. You should constantly remember the fact that galaxies are good tracers of the underlying large scale structure, but they are biased tracers of the underlying dark matter distribution. So mass to light ratio is not constant, where mass now includes the total mass, including the dark matter. That is not constant everywhere in the universe. So long as you remember that, you can use galaxies as biased tracers of the underlying matter distribution as well. You need to do that because, see, remember when you do these numerical simulations, cosmological simulations of dark matter, you get the cosmic web, but you don't know where the galaxies are. And by comparing simulations, while comparing to simulations to actual galaxy distributions in 3-dimensional space, you have to account for this galaxy bias. So galaxy bias refers to the ratio of baryons to the ratio of dark matter in any given volume. Okay, so at high densities you may have one ratio of one value for the galaxy bias. At low in group densities you may have a different value. In the field you may have a different value. In the void you may have a still more different value, and so on. Okay, so we will stop here and take any questions on today's class or previous classes, and we will continue with. So we are now done with looking at these components purely from imaging point of view and trying to use galaxy images to measure things about their galaxy, either both qualitatively and quantitatively. We are done with that. We won't go back to that. Now we will study other aspects of galaxies, starting with the large scale structure of galaxies. How do supermassive, that I will cover when I talk about galaxy formation. So we'll come to that in one of the later lectures. Although in detail, you may have to study that in your AGN course, because your AGN course, which will come in the next quarter, is all about supermassive black holes and their activities. Yeah. Yes. Yes. You are biased towards particular scales, but the idea behind all of these measurements is that everybody should be biased in the same way. So if we go back to your, yeah, I mean, you will frequently encounter this in astronomy, okay, that every measurement you make, I mean, this is the fundamental difference between astrophysics and laboratory physics. In the laboratory physics, all measurements, everything is controlled. You change one parameter, then study the effect on another parameter. In astrophysics, you can't change any parameter. Okay, your measurements are all incomplete. So it is like a laboratory experiment in which you are given some random data. Okay, I did this and that happened. I did this and that happened, without any control parameters which lie in your hands. You may be able to measure the value of those parameters, all of which are changing. So you have to figure out what is going on based on this kind of chaos. In addition to that, the information is incomplete. Okay, so you can only, for example, we can measure things in detail in the nearby universe. Once we go to the high redshift universe, all our information is very incomplete. Secondly, we have random biases, which means we are measuring low signal to noise measurements. So the reliability of the errors on our measurements are very large. Sometimes so large that you don't know whether the value is 0 or some non-zero. It is that large. And so because of this, the way you are used to in thinking in physics, that okay, keep everything constant, change one parameter, then see the effect, so it is very unlikely that we will discover new laws of physics in astrophysics, because it is complete chaos. There is all mayhem. But it can be, knowing the laws of physics, one can apply them to astrophysical situations to understand the reality. So you can move only in that direction. You cannot move very easily in the opposite direction. Maybe with, I mean, see that there were two hopes that with dark matter and dark energy, we will discover some fundamental new physics. We have not yet discovered that physics. We're trying, but so far all the progress in the last 100 years has been in the application of existing or known physics to astrophysical situations. Yeah. Okay, so to come back to your question, you were asking about clumpiness. Right, you are asking about clumpiness, right? Yeah. So here I've said that to measure clumpiness, we convolve the galaxy image with a boxcar function of width 0.25 Petrosian radius. So this is where you need the consistency. So it will be biased, but if you make a measurement and if I make a measurement, both of us will be biased in the same way, and therefore we can make a comparison. So what you are not allowed to change is you can't say I don't like 0.25, I'll do 0.3 or 0.35. That you can't do. That's all. You can do that. So for example, you could just take a Fourier transform and see where the peaks are in the power spectrum. That will give you the angular scales on which things are clumped all at one go. But here the purpose is not to find the scale of the clumpiness, but only to quantify how much clumpiness there is. So what you're trying to do, suppose you know for some reason that the effect you're looking for will produce clumpiness on scales of 100 parsec. Then you can convolve with that kind of function to find those features. But if you're doing it completely blind, you do it in a sort of scale-free way, and you do it in a biased way, but everybody should have the same bias. So I've given links to all the original papers for CAS, and I don't know whether I have given for CAS. Yeah, I'll add some papers here. I'm not cited the CAS papers, but I've given you references to the GM papers. So this is the main reference, Lotz et al. 2004. where the Gini coefficient and the M20 parameter were introduced. Okay. Yes. So if there are no further questions, we will stop and we will meet again at the regular slot on Monday.